Hello everyone, myself Sai from CSIT. Today in this presentation, I am going to explain about the topic adsorption mechanisms of heavy metal ions from drinking water by weakly basic anion exchange resins. And this presentation contains the abstract introduction, principle of adsorption, materials and methods, the result, followed by conclusion and few references. If we look at the abstract, heavy metal microcontaminants can be removed from water sources such as rivers and lakes using variations of conventional treatment technologies. Weakly basic anion exchange resins offer the best ability to remove trace amounts of heavy metals with high selectivity. This paper discusses how weakly basic resins absorb heavy metals using two different approaches. The removal of mercury, cadmium, and lead ions is based on the fundamental theory of coordination chemistry. The mechanism is not exchange but extractive adsorption of heavy metal salts. However, the marked preferential adsorption of chromate by weakly basic anion exchange can be explained using the traditional theory of ion exchange. A lab scale study produced positive results for the removal of trace amounts of heavy metal ions from drinking water. Followed by introduction. Wastewater of mineral processing industries normally contains a variety of hazardous heavy metals and sometimes may be discharged without adequate treatment. The polluted drinking water source contains heavy metal contaminants, normally with a concentration up to 100 grams per liter. The normal cation exchanger cannot exclusively remove heavy metals due to the exchange competition with alkaline and alkaline earth metal ions. Principle. A possible way to eliminate trace amounts of heavy metals is by introducing weakly basic anion exchange resins. The functional groups of these resins are chiefly primary, secondary and tertiary amino groups. Using a primary amino group as an example, the equilibrium does exist at neutral pH. The principles used are the principle of extractive adsorption. Using a primary amino group as an example, the equilibrium does exist at neutral pH. In addition, because this process is not an exchange of ions using mercury chloride as an example, the process can be written as the following equation. As the stability of the Me nitrogen bond is lower than that of nitrogen hydrogen bond, consequently, the degeneration of the resin can be achieved by applying a strong acid. The resin cannot be reused directly for adsorption of heavy metal salts. You can check the equations for absorptions for the given metals in the equations above. Now let's move to the second principle. The principle was the principle of ion exchange. In natural water and at neutral pH, chromium salts usually occurs as CrO2 and HCrO, which cannot be eliminated in the same way as explained above. The use of weakly basic anion exchange resins has been tested for the removal of chromium for a neutral pH condition. Assume that the elimination of HCrO species by introducing resin in the hydrate form can be written as the following equation. This process is not extractive removal of heavy metals but the removal by ion exchange. For generation, the exchanger can be converted to hydrate from by the means of caustic, alkali or lime. The next followed topic is materials and methods. Weakly basic anion exchange resins. Before the experiments, the resin should be pretreated with hydrochloric acid and sodium hydroxide to remove impurities. After rinsing by means of demineralized water, the resins can be applied for the treatment for drinking water. In the experiments of 4 kinds of commercial weakly basic anion exchange resins were applied for the removal of heavy metals from drinking water. Test installations. The resin material was packed in a filter column with an inner diameter of 2.8 cm and a length of 28 cm. The raw water was first pumped to an intermediate buffer vessel and then it flowed through the filter in the downstream direction. Samples were automatically taken from the effluent. The pH was measured and recorded automatically. Effluent sampler, the flow rate amounted to 20 BV. BV is the bed volume based on the empty filter volume. Let's discuss about the adsorption equilibrium. The equilibrium experiments were carried out for static conditions. Samples of resin material were soaked with 200 milliliters cadmium to bearing original solution. After equilibrium was established, 48 hours in vibration machine, the solution was analyzed for heavy metal concentration. The equivalent fraction of heavy metal in the resin phase was determined by the difference between initial and equilibrium concentrations, followed by the analytical method. Heavy metal concentrations were determined by the means of flame atomic adsorption spectroscopy using a variant spectra instrument, which is detection limits of 0.001 milligrams per liter cadmium, 0.01 milligrams per liter lead, and 0.0001 milligram per liter mercury. Effluent pH values were monitored using standard Scott electrodes and a Kick digital pH meter 646. Concentrations of organic matter expressed as DOC were measured by Shimazu DOC 5000 analyzer. Let's move to the results. The first result was extract removal of heavy metals based on the theory of coordination chemistry. Trace amounts of heavy metal ions were removed with high efficiency. However, the concentration of other background components were little after treatment. The same results were also observed for resin material, duolite A7, which suggests that weakly basic anion exchange resin exhibited highly selectivity for trace amounts of heavy metals without significant change of the water composition. Followed by the next result, removal of chromium based on the theory of ion exchange. With the increase of SO4 in the original solution, the rapid decrease of equivalent fraction of Cr in exchanger phase can be observed. Furthermore, breakthrough curves of chromate were obtained using the small column with an inner diameter revealed the great difference with the non-buffered demineralized water as a raw water. The adsorption of chromium is affected by the increased sulfate concentration. This is very different from the case of removal of cadmium from water, the presence of chloride. And the following result is regeneration. Different adsorption approaches, extractive adsorption or adsorption by ion exchange, lead to different regeneration processes as described by the formulas above. The regeneration of Cr loaded exchanger, however, the bulk part of Cr was eluted by treatment with sodium hydroxide, and the treatment with sulfuric acid was not necessary. The whole regeneration process can be completed by the consumption of 4 BV or 4% of sodium hydroxide. The amount of chromium is approximately equal to the amount adsorbed in the service cycle. Let's move to the conclusions. The application of commercially available weakly basic anion exchange resins allows extremely selective elimination of trace amounts of variety of hazardous cationic heavy metals and the elimination of chromate anions from raw drinking water supplies. Trace amounts of mercury, cadmium and lead were removed by weakly basic anion exchange resins with the formation of a coordinate covalent bond. Different adsorption approaches lead to different regeneration processes. Hg loaded, mercury loaded resins need 4 BV of sulfuric acid solution for complete reclamation and the same amount of sodium hydroxide for neutralization. However, the resin loaded by Cr chromium, only sodium hydroxide can lead to an almost complete regeneration. You can also study much deeper about the adsorption of metal ions through these references given in this page. And these are, you can collect the very information. If you are really interested, you can try these references and you can go much deeper into the topic and try to, if you are interested in that, if you are interested to solve the problems much deeper, you can try. That's the end of my presentation. Thank you for everyone for patiently listening my speech. Once again, thank you everyone.